Hello and welcome to section 6.4. So this video is a lecture video for logarithmic functions. Alright, so the logarithmic function is the inverse of the exponential functions. So we learn about them together with exponential functions because the logarithmic functions will help us solve exponential equations that arise in application problems that we'll see in the last section of this chapter. So we're going to talk about, let's look at the definition of a logarithmic function with base a. So this is the same base as we encountered in exponential functions. So base a, the base has to be positive and not equal to 1. So we're going to look at bases that are bigger than 1, exponential growth, and less than 1, exponential decay. And we define the logarithmic function as y equals log of base a of x. So y is the logarithm with base a of x. So basically this is a rewrite of an exponential function. So y equals log of base a of x if and only if x equals a to the y. Okay, so you can see how things correspond with each other. So this is called the logarithmic form, and this is called the exponential form of the same relationship, of the same equation. So the bases are the same. So this is the base of the exponential is the same as the base of the log. But like the x's and y's are switched around, and logs and exponentials are inverses of each other. So basically, the places switch around. Okay. So here the y is what you're solving for, and here x is what you're solving for. Okay. Y is the exponent in the exponential, and x is like what's after the log, or you're taking the log of x. Alright. Now the domain of a logarithmic function, you need to have x's positive values. So because the range of an exponential is all positive y values, the domain of an exponential is going to be all positive values. So if you take your calculator and you plug in any negatives or 0 in here, you're going to get a domain error because you cannot take the log of a 0 or negative values. You can only take the logs of positive values. So for a logarithmic function, the domain is restricted to just positive values. Alright, so we're going to do some practice. We're going to change form. So change form from exponential to logarithmic form. So we're going to use these relationships here. Alright, so let's see. Part A says 16 equals 4 to the 2. Okay, so when you change it to logarithmic form, the exponent part goes by itself, 2 equals. The base will stay the base. So this is log of base 4 of 16. Right? So whichever number is left over, you write after the log. So the exponent goes by itself, and that equals to log of the same base as the exponent of the number 16. Okay, of the answer. Alright, 3 to the x is 4.6. So here we have the exponent x equals log of the base 3 of the answer, of 4.6. Part C, so you look, the exponent 3 equals log of the base of the exponential, which is a, of 2.1. D, we have the exponent 2.2 equals log of the base e of the number a, m. Alright, and that base e log is special. Okay, so we have what's called the natural log. The natural logarithm is log base e of some quantity, the log base c has a special name. This is ln. Alright, so ln is called the natural log, and it's the log with base e. So sometimes, or most of the time, you'll see this as written instead of log base c is going to be ln, natural log of m. Alright. There's another special log, log base 10 of a number is just written as log a. So if the base is missing, then automatically you need to assume that it's a base 10, right? Okay, so let's look at example 2. So we're going to change from logarithmic to exponential form, again using these conversions. But now we're going to go backwards. So again, sort of the base will stay the base, but the numbers will switch around. Okay, so like the answer becomes the exponent. So we have the base of 3 to the exponent of -2 equals the number 1/9. Now you can check out, yeah, this is true. Okay. Part B. So the base b to the exponent of 2 equals 4. Okay. So we're changing form. Some of them you can go, yes, I agree, this is true. Some of them, you can see that when you change form, it helps you solve the equation, right? B squared equals 4, and you can figure out that b equals plus or minus 2. Because the base of an exponential or log can only be positive, then you just take the positive answer. Okay, so this changing form helps you solve equations. Okay. Alright, let's do part C. Log base 2 of 6 equals x. The base of 2 to the exponent of x equals 6. Alright. ln of x equals 4. ln means log base e. So put in the base. So the base to the exponent e to the 4 equals to x. Alright. Let's evaluate. So we're going to use these properties of logs to evaluate without using a calculator. So we have base, log base a of 8 equals a number. We're trying to figure out what the number is. So let's change this to exponential form. So we have the base 8 to the x equals to 8. And we can match bases. This is 8 to the 1, so we get x equals to 1. Okay, we'll see that what happens is that you can match bases to the log. So you have, if you have log base 8 of 8 to a power, then like the log with the same base cancels the base of the exponential, and you get x equals 1. So you can sort of, this is like the long way of doing it, change it to exponential form, but sometimes you can take a shortcut. If the log of the base with that base matches the base of the exponent that you have, then you can cancel them out. Okay, part B. Log base 3 of 1/9 equals x. We're trying to figure out what it is. So 3 to the x equals 1/9. Change this to a base of 3. So 3 to the x equals 3 to the -2. The bases match, so you get x equals -2. Right. And the shortcut for this would be to have log base 3, 1/9 is 3 to the -2. You write it so the base of the log matches the base of this exponential, then you cancel and you get the answer is -2. Alright, part C. Log base 1/3 of 9 equals an unknown. So let's write to an exponential form. 1/3 to the x equals 9. Let's change both of them to base 3. So we have 3 to the -x equals 3 to the 2. Bases match, so x equals -2. Alright, let's look at this one. Log of cube root of 100 equals an unknown. Log without a base means log base 10. 100, cube root of 100 means 100 to the 1/3. Now let's change to exponential form. 10 to the x equals 100 to the 1/3. change this so it's base 10. So 10 to the x is 10 to the 2 to the 1/3. So 10 to the x equals 10 to the 2/3. Bases match, so x equals 2 to 2/3, like this. Okay, now let's look at domain of a logarithmic function. So with the log, no matter what basis, we need this whatever quantity that goes after the log or in the parentheses with the log, we need this to be positive. So it can't even equal to 0. So you need to take the argument of the log and set that bigger than 0 and then solve. So we have x is bigger than 1. So the domain is all the values of x that are bigger than 1. So those are the only ones you can plug in to evaluate. If you plug in 1 or lower, you're going to get a domain error in your calculator. All right, so part B, our function is 8 plus 5 log of 2x plus 3. To find the domain, you only need to look at the log part. So we need 2x plus 3 to be bigger than 0. So x has to be bigger than negative 3 over 2. So the domain is all the values of x bigger than negative 3/2. All right, let's look here. So we need this to be bigger than 0. All right, which happens, 1 is positive always, so we need x minus 1 to be bigger than 0, which means x has to be bigger than 1. All right, so that's the domain. All the values of x have to be bigger than 1. That will work. Let's look at D. So we have 1 over natural log of x. First of all, we need x to be bigger than 0 for the log to work. All right? And also because the log is in the denominator, we need to figure out when log of x equals to 0 because we can have that happen because we don't want to divide by 0. Okay, so let's put the base in. So let's change this to exponential form. So x can't equal to e to the 0. Any number to the 0 is 1. So x can't equal to 1. So the domain is the combined domain of these two. So x has to be bigger than 0, but excluding 1. So it's all the numbers from 0 to 1, and then from 1 to infinity. Okay? Alright, so let's look at evaluating using the calculator. So if you look at a calculator, at our functions, let's do the Desmos calculator, you see most calculators have the natural log and the log base 10 in it. It doesn't have any other bases. And we'll find there is a change of base formula that we can use to figure out logs of other bases. For now, in these problems, we're just asked to do the natural base and base log base 10. So we can just plug things in the calculator as you see them, using parentheses and things like that. So let's do part A, log of 2/3 divided negative 0.1. So we have natural log of 2/3, and then all this divided by negative 0.1. Oops. 4.055. All right, round to 3 decimal places. All right, let's do this one. So we have 3 log is log base 10 of 80 minus 5. So I'm going to clear this, do a big parentheses to have the top in the big parentheses. So we have a log of 80. Let's go outside the parentheses. Minus ln of 5. So minus, oops, this needs to be in the parentheses. minus ln of 5, okay, divided by, good big fraction there. Did I forget a 3? I did, I forgot a 3 here. All right. Log of 5 plus ln of 20. So function log of 5, oops, I'm in the wrong place. Log of 5 plus natural log of 20. Let's check to see if that's all right. There we go. 1.110. Alright, so just evaluating, you can use the natural log or the log base 10 in your calculator. Just you can input everything at once, just make sure that it goes in the right place, using parentheses and things like that. Okay? Alright, let's graph log functions. Okay, so to graph a log function, you want to base it on the exponential function because they're inverses of each other. Okay, so exponentials and logs, so 3 to the x is an exponential function and log base 3 of x, it's its inverse. Okay, so you basically want to make the table or the graph for the exponential function. This is an easy one to do because evaluating exponentials is straightforward. So 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9. Right? Now 3 to the negative 1 is 1/3. 3 to the negative 2 is 1/9. Okay, so the log is you're going to switch the columns. Okay, so basically your x becomes your y and your y becomes your x. Right, so these x values go in the y column and the x values, the ones in the y column, go in the x column. All right, and now you're basically, when you do this, you're graphing log base 3 of x. All right, so exponentials and logs are inverses of each other. So do the table for the exponential and then switch the columns, and that will give you the table for the logs. Okay, so let's graph both of them on the same graph. So the exponential is going to be 0, 1, 1, 3, 2, 9, 1/3, 1/9. It has a horizontal asymptote at y equals 0. And let's draw the graph. So it hugs the x-axis and then it shoots up. This is 3 to the x. Right, now for the log graph, the horizontal asymptote is going to turn into a vertical asymptote because x and y switch. So this is an asymptote at x equals 0. And then let's graph the points. So when x is 1/9, we get -2. When x is 1/3, we get -1. When x is 1, we get y 0. X is 1, y is 0. X is 3, y is 1, and x is 9, y is 2. So we can graph the log base 3 function, and it looks like this. So it hugs the vertical asymptote, the y-axis, and this is log base 3 of x. Okay, we can see that these are symmetric along the diagonal line y equals x. Right, so this is what a parent log function looks like. So it's the exponential reflected over the diagonal line. Alright, let's look at the next one. So we're going to do the same thing. 1/3 to the x and log base 1/3 of x. So let's do the table for the exponential function. Y equals 1/3 of x. Okay, so we're going to pick 0, 1, 2, negative 1, negative 2. 1/3 to the 0 is 1. 1/3 to the 1 is 1/3. 1/3 to the 2 is 1/9. And I'm expecting the values to decay because the base is less than 1. 1/3 to the negative 1 is 3 to the 1. 1/3 to the negative 2 is 3 to the 2, which is 9. So it starts high and then it goes low. Okay, so this has a horizontal asymptote at y equals 0. And then we're going to plot the points. Y-intercept is as 1, and then negative 1, 3, negative 2, 9, 1 and 1/3, 2 and 1/9. Here's our exponential function with the horizontal asymptote. So this is 1/3 to the power x. All right, now for our log function, the horizontal asymptote becomes a vertical asymptote at x equals 0. So the x's and y values switch around, and we're going to make the table log base 1/3 of x. You fill the table by not calculating, by switching the columns. Okay, so the x's go in the y column, and the y's go into the x column. And this is because the log is defined as the inverse of the exponential. All right, so 9 gives me negative 2. 3 gives me negative 1. 1 gives me 0. 1/3 gives me 1. 1/9 gives me 2. All right, so we can draw this. Goes like this. And then it hugs the vertical asymptote like this. So this is log base 1/3 of x. And as with the other problem, you can see that these are mirror images, they're inverses, so they're mirror images of each other along y equals x. Alright, so that's the best way to graph the logs, is to graph the exponential and then switch them around. Alright, let's graph a couple more log functions. Now basically kind of having the picture of the log in our minds, right, and then doing transformations. Alright, so here a log base 2 of x minus 3. So this is a shift of 3 units to the right. Okay, so let's plot log base 2 of x and then do the translation. Okay, so this is the inverse function of 2 to the x. So kind of imagine picking x values here. So 0, 1, 2, 3, negative 1, negative 2, negative 3. And doing 2 to the x, but you're putting in the wrong column, right? So you're putting x's go in the y's and y goes into the x's. So 2 to the 0 is 1, 2 to the 1 is 2, 4 and 8. And here we get 1/2, 1/4, 1/8. Right, so we have a vertical asymptote at x is 0. And then we're going to graph 1, 0, 2, 1, 4, 2, 8, 3, and then fractions on this side. Okay, so this is log base 2. All right, now let's transform it. So the x minus 3 is moving everything 3 units to the right, including the vertical asymptote. So the vertical asymptote moves here at x equals 3. And then you add 3 to all the x values. Okay, so 1, 0 goes to 4, 0. 2, 1 goes to 5, 1. 4, 2 goes to 7, 2. All right, and what was the next one? 8, 3 goes to 11, 3. All right, so we can do these, and then make sure the graph goes next to the vertical asymptote like that. So this is log base 2 of x minus 3. Alright, so let's answer some questions. Okay, so the domain of the function is going to be, you look here, it's going to be x is bigger than 3. Alright, you can see that there's a vertical asymptote at x is 3, and all the values of x that I picked were bigger than 3. We graphed it. I determined the range and the asymptote. So this is the graph. See, the range is going to be negative infinity to infinity. And there's a vertical asymptote at x equals to 3. Alright, now the inverse of this, right, is going to be, so we have y equals log base 2 of x minus 3. So we're going to switch x's and y's, and we're going to change this to exponential form. So 2 to the x is y minus 3, and y equals 2 to the x plus 3. Okay, so this is the inverse of the original function. Alright, so the domain and the range of the inverse are going to be the range and the domain of the original function. So the domain is negative infinity to infinity, and the range is y is bigger than 3. Right? Graph the inverse. So to graph the inverse is basically the exponential 2 to the x shifted up 3 units. So it's basically these values, this is 2 to the x, and then you need to add 3 to each of these. Right? So we're going to have a horizontal asymptote at y equals 3, because we're shifting up. And then we're going to have 0, 4, 1, and 5, 2 and 7, and so on. Okay, so this is 2 to the x plus 3. Right, so this function here and that log base 2 of x minus 3, they are inverses of each other, reflection across that line. Okay, let's do the next one. Alright, so A. So we have negative log base 2 of negative x. Okay, so the domain is if negative x is bigger than 0, which means x is less than 0. So it's all the negative values. Okay, we're going to graph. Alright, so let's try to remember what the log looks like. So the log has a vertical asymptote at x equals 0. Alright, and log base 2 of x, right, is 1, 0, 2, 1, 4, 2, and 8, 3. Looks like this. Okay, so I'm just gonna hold that in your mind. We can erase it later. So we have two negatives. So this negative reflects it across the y-axis, and this one reflects it across the x-axis. So it's two flips. Okay, so we're going to have the reflection across the x-axis is going to do this to it. So this is log base 2 of negative x. And then if we put a negative in front of it, it's going to flip it over the y-axis. So it's going to do this, and this, and this. Is 8. Alright, so we're going to have this right here. This is going to be log base 3 of negative x with a negative in front. Right, so I'm going to get rid of some of this stuff because it's getting too busy. That was the original log function. And this one was reflected across the y-axis. Right, so this is what we want. 2 reflections. Right. Okay, so that was from the graph. Determine the range and any asymptotes. Okay, so the range is negative infinity to infinity. There's a vertical asymptote at x equals 0. All right, D is find the inverse. Okay, so we have y is negative log base 2 of negative x. Let's get another color. Switch x's and y's. X equals negative log base 2 of negative y. We got to solve for y. Negative x equals log base 2 of negative y. Change it to exponential form. 2 to the negative x equals negative y. So y equals negative 2 to the negative x. Right, so now we have to graph this. Right, so this is the exponential function 2 to the x, which looks like that, reflected across the y-axis, which is going to look like this, and then reflected across the x-axis, which is going to look like this. Right? So that's what we're looking for. Okay? So we have 0, negative 1, and then we have some fractions here. And then we have negative 1 and 2, negative 2 and negative 4, negative 3 and negative 8. It's all powers of 2. Right? And this has a horizontal asymptote at y equals 0. So this is negative 2 of negative x. Alright, the domain and range of the inverse. So that's going to, this is f. Alright, so now we're looking for E. So the domain and range of the inverse are going to be the domain and range of, this is the domain of the original switched over. Okay, so the range is going to be x is less than 0, and the domain is going to be negative infinity to infinity. All right, let's do another one. So first find the domain. So we're looking here. We want x plus 1 to be bigger than 0, so x is bigger than negative 1. Right? It's going to have a vertical asymptote there at x equals negative 1. Okay, so let's make the vertical asymptote right here. Right? Let's see what's happening. So this is log base 3. And we have a shift to the left of 1 unit, which goes with the vertical asymptote. There's a reflection across the x-axis, and there's a vertical shift. Okay? So we reflect and we shift. Okay, so first of all, log base 3 is going to look like this. So 1, 0, a 3, 1, and then 9, 2. So this is the original log base 3 of x. Right? Then the minus means that it's going to be reflected across the y-axis. So it stays here, but then it goes to negative 1 and negative 2. So it's going to look like this. So this is negative log base 3 of x. Right? Then we want to shift it 1 unit to the right and 2 units up. Okay? So let's see, this point right here, which is 1, 0. This is going to shift 2 up and 1 to the right. So it's going to go here. This point right here, which was 3, negative 1, is going to go to 1 and 1. This point right here, which is 9 and negative 2, goes 8 and 0. Alright, and let me erase everything else. Alright, let's see. Okay, so 1, 0 went to 0, 2. 3, negative 1. So we need to go 2 and 1. And 9 and negative 2. We need to go 8 and 0. Okay, those are my points. And so this is going to be like this. Okay, so this is 2 minus log base 3x plus 1. Alright, this is B. So the range is negative infinity to infinity. We know there's a vertical asymptote at x equals negative 1. That's when this is equal to 0. Alright, let's find the inverse. Okay, so the inverse, we start with y equals 2 minus log base 3 of x plus 1. Switch x's and y's. X equals 2 log base 3 of y plus 1. X minus 2 equals negative log base 3 of y minus 1. Multiply by negative 1, so negative x plus 2 equals log base 3 of y minus 1 plus 1. Change it to exponential form, so 3 to the negative x plus 2 equals y plus 1. So y equals 3 to the negative x plus 2 minus 1. I'm going to write it as 3 to the negative x minus 2 in parentheses minus 1. Alright, so the inverse is an exponential. So the domain and range are going to be the range and the domain. So this is the domain of the log. So the range is going to be x is bigger than negative 1. And the domain is going to be negative infinity to infinity. Alright, so because everything switches, this one had a vertical asymptote at x equals negative 1. So this one is going to have a horizontal asymptote at y equals negative 1. Alright, and you can sort of graph this, or you can look at your points that we had on the log functions and switch the x and y values. That's probably a bit easier to do. So this point here is 0, 2, so we need the point 2, 0. This point here is 1 and 2 and 1, so we need 0.12. Alright, and this point here is 8, 0, so we need 0.08. Alright, so we try to draw, so here's the horizontal asymptote, and then this goes up to here, and then past that. Let's try again. All right. There you go. So we have this. It doesn't go there. Oh my goodness. Okay. It goes here, it goes here. 2, 1 is 1, 2. No, it goes here. And 2, 0. Okay, so it's this, this, and this. That makes more sense. There we go. Okay, so this is 3 to negative x minus 2 minus 1. That's the graph of the inverse. All right, cool. All right, so last little bit in this section, we're going to solve logarithmic equations. So the best thing to do is change them to exponential form. Okay, so part A, we have log base 5 of x equals 3. We're going to write this as 5 to the 3 equals x. So 5 to the 3 is 125. So our answer is 125. Let's look at B. Change this to exponential form. So we have 3x minus 2 is 3 to the 2. 3x minus 2 equals 9. 3x equals 11. So x equals 11 over 3. Now let's look at this. So this one, we don't want to change it to exponential form because it's going to make it more difficult. We want to see if we can simplify this. So I have log base 6, 36 means 6 to the 2. And if the bases match, we can cross them out, and we just get 2 equals 5x plus 3. So negative 1 equals 5x, so x equals negative 1 over 5. Now let's look at this one. Change this to exponential form. So we have x squared plus x plus 4 equals 5 to the 2. X squared plus x plus 4 equals 25. X squared plus x minus 21 equals 0. And I don't think this factors out. 7 times 3. So we use the quadratic formula. We have negative 1 plus or minus 1 squared minus 4 times negative 21, so plus 84 divided by 2. Negative 1 plus or minus square root of 85 divided by 2. So here are our solutions. All right, and that's it for this section.